All right, one more video dealing with antiderivatives. This one hopefully will be a little bit quicker. What we're going to talk about here are trig and inverse trig functions. So a lot of this will be, hey, remember this in 251? Here's the 252 version. For example, y equals sine of x is a function that you ran across a lot in Calculus 1, and if you were asked to take its derivative, hopefully by the end of the class you knew that the derivative of y equals sine of x is y equals cosine of x. And sometimes you'd even take the derivative of cosine of x, and maybe you knew that the derivative of cosine of x was negative sine of x. And you continue going, the derivative of negative sine of x, well, if you treat that negative like a constant, negative 1, you can pull it out in front of the derivative sign. The derivative of sine is cosine, so the derivative of negative sine will give you negative cosine. And you can do that one more time, take the derivative of negative cosine, you'll get all the way back up to sine of x. If we are taking derivatives, we have this nice little cycle going on here for our basic trig functions. Well, it stands to reason that if this cycle works for derivatives, the kind of cycle in reverse is going to work for antiderivatives. What I'm saying is if anybody gives you the function sine of x and asks you for its antiderivative, well, the answer to that question would just be negative cosine of x. And that's kind of by definition. We just said a minute ago that the derivative of this guy was this guy. Therefore, by definition of antiderivative, the antiderivative of this guy would have to be this guy. And the logic continues to hold around the circle. And we kind of get something that goes like this when we're talking about antiderivatives. It's worth pointing out that in Calc 1, you could do a lot more stuff. Somebody could ask you for the derivative of sine squared x, for example, and you could use the chain rule and figure this out. Unfortunately, that logic doesn't work at this point in the class. We do not know how to take the antiderivative of sine squared x, so I'll leave that as a question mark for now. Similarly, you could use the chain rule if you had a function like e to the x nested inside the cosine function. That's something we could easily take the derivative of, or at least we could. I don't know if it's easy. But we cannot take the antiderivative of it. And you're like, oh, okay, so this is all that I need to know up here are just these things, huh? No, unfortunately, that's not quite it. Let me show you a couple of examples. Here's kind of a tricky one. You're asked to figure out the antiderivative of 3 over the secant of x. And you're like, I don't remember secant of x being an answer in Calc 1. You might be like, the derivative of secant is secant times tangent. If you remember that, that's great. We'll return to that in a couple of minutes. But we don't remember, we never got 3 over secant of x as an answer in Calc 1. So you might wonder what you can possibly do with this question in Calc 2. Well, it turns out that this is one of those cases where you have to kind of algebraically rewrite this so that it fits a form that you recognize. Secant is the reciprocal of cosine. So 1 over secant is the same as cosine. What I'm saying is 3 divided by secant of x is the exact same as 3 times cosine of x. And maybe if you have it written in this form, you could figure this out. If you want, you could write 3 out in front of the integral and then take the antiderivative of cosine of x. Or if you're really good with these at this point, you might just be able to look at this and be like, well, the antiderivative of cosine of x is sine of x. So this answer here will be 3 sine of x, and then tack on the plus c to make it a general antiderivative. But since we mentioned secant, maybe we should kind of follow that thought through. You were asked for the derivative of secant in a Math 251 class. Maybe you remember it, maybe you don't. Here's this kind of recall from 251. I bet at one point in your Calc 1 class, you had to come up with, or at least use, all 4 of these facts. They're good ones to get students to practice with trig identities and with the quotient rule. Tangent, that's just sine over cosine. Well, I can use the quotient rule on sine over cosine, and I can use the Pythagorean identity to simplify this, and I end up with 1 over cosine squared, which maybe I recognize can be written as secant squared. I bet you did all 4 of these in a Calculus 1 class at some point. Turns out that 2 of the 4 will end up being relevant for Calc 2. Right? There's really 6 trig functions, sine and cosine, which we already talked about, secant, cotangent, and tangent, these guys here. This statement and this statement will end up being relevant later on in the class. So these top 2 statements imply these bottom 2 statements, right? If the derivative of secant is secant times tangent, then the antiderivative of secant times tangent would just be secant of x plus c. Similarly, the derivative of tangent gives you secant squared. The antiderivative of secant squared gives you tangent of x with the plus c's in there. And so while I could come up with 2 more statements for these guys, they won't be relevant later on in the class. So try to keep your list of stuff you need to know as short as possible. Let me add these 2 to your list. Quick example with these. Suppose you were asked this question. The antiderivative of 5 times the tangent of x divided by 3 times cosine of x. Well, if you look at this, it's tempting to kind of be like, what's the antiderivative of the top? What's the antiderivative of the bottom? Remember that you cannot do that. The same reason that we needed the quotient rule in Calc 1 will mandate that we have some other rule in Calc 2 that we haven't learned yet. So all you can do right now is rewrite this in such a way that maybe it's the same as something you already know. And there's not that much stuff as far as trig functions that you already know. Maybe if you play with this a little bit, you'll be able to figure out that this is just 5/3, this 5 and this 3, times tangent of x times secant of x. Why is that true? Well, secant of x is 1 over cosine of x, so this cosine of x turns into this secant of x, and then the 5 and the 3 are both just constants, so I can think about it as 5/3 times this whole thing. Now when I take the antiderivative, I can pull the constant out in front, and so I just get 5/3 times the antiderivative tangent of x times secant of x, and as we just wrote a minute ago, the antiderivative of tangent of x times secant of x is just secant of x plus c. So what we get here is 5/3 secant x plus c. That's all I've got on trig functions. However, I do have another one of these recall from Calc 1 things. In a Calc 1 class, odds are you also memorize the derivatives of some inverse trig functions. These come into play when you're trying to teach students what's called implicit differentiation. It's kind of a clever way you can derive these guys. I think it's kind of fun personally. It doesn't matter whether you do or not. At any rate, there's at least 3 of these guys. If your teacher's really ambitious, you might have 3 more for arc cosecant, arc secant, and arc cotangent. At any rate, much like we had up here, not all of these will end up being necessary for you to know in Calc 2. Only some of them will come into play with the methods we learn later on in this class. In this case, we're only going to need 2 of them, again. So we're going to need to know the analogs of these 2 statements. You won't need arc secant, arc cosecant, and arc cotangent, which is why I didn't even write them. And it turns out you won't even need arc cosine of x in this class either. Just the analogs of the top and the bottom statement. So these 2 statements about derivatives imply these 2 statements about antiderivatives. If you ever are asked the antiderivative 1 divided by the square root of 1 minus x squared. And I know that seems like a very specific thing. So what are the odds you'd ever run into exactly that? And frankly, it is pretty unlikely. At this point, maybe someone just gives you exactly that and you recognize it. Later on in the class, we'll do some transformations to get things to fit this form. At any rate, if you ask the antiderivative of this guy, just know it's arcsine. If you ask the antiderivative of this guy, just know it's arctangent. And for what it's worth, most students don't remember these at all. And they go through them and they're trying to think power rules and all these other things. And they're like, oh man, that's one of those inverse trig ones, huh? And then they open up their book and they're like, is this the arc sine or the arc cosine one or whatever? If you can memorize them, great. Eventually you'll have them memorized because there's only 2 of them. But if you don't have them right off the bat, don't feel bad. I bet a lot of your classmates don't have these memorized as well. Quick example with one of these guys. Suppose you ran into this problem. The idea is you look at this and you're like, oh man, that doesn't fit any form that I know. I don't know what to do with that guy. Power rule seems really challenging. Maybe you do some bad algebra and write this as 2x to the negative 2, and I don't know what the heck you do with this. That doesn't work out algebraically. But maybe eventually you'd be like, you know what? That's really similar to this. It's almost the same, except I have these extra 2's and 2's here. In fact, I suppose I could factor out a 1/2, in which case what I would have left is 1 divided by 1 plus x squared. And I know that it's not obvious, it's not supernatural to go from here to here, but if I start you out with this, maybe you'd multiply the fractions, and then you'd be like, wait a minute, I have 2 terms here, so this 2 has to get distributed through and hit both the 1 and the x squared. Maybe that justifies how I was able to pull out the 1/2 in the first place. At any rate, if you can pull out that 1/2, that 1/2 is just a constant, goes out in front of your integral sign, and then when you take the antiderivative of 1 over 1 plus x squared, you just have memorized that that is the arctangent of x, tack on your plus c, and you call it a day. That's all I have for inverse trig functions. I got one more thing. You're like, man, you keep having one more thing. I saved the best for last. One more recall from Calc 1 that's going to give you a statement in Calc 2, and it's going to be the simplest thing you've ever seen. You're going to even think it's kind of funny. Funny is probably not the right word. I'll squeeze it over here. It's that the derivative of e to the x, remember this one? It was just e to the x. So what's that going to tell you? Well, this is your favorite thing in Calc 1 because it was super easy. There was no work to do. It's your favorite thing in Calc 2. I'm having a hard time talking. There's nothing to do. If the derivative of e to the x is e to the x, then the antiderivative of this e to the x over here is this e to the x over here. If you're asked for the integral of e to the x dx, your answer is just e to the x plus c. That's simple enough that I'm not even going to bother putting it in as a 4th example because this is getting pretty filled up. It's just something that I wanted to tack on. FYI, if you want a nice little summary of these, like if you think of what we've done in this section, we talked about the power rule, some other rules, this natural log stuff. We've talked about a lot of stuff. On page 318 of your text, they have this fancy little table here at the bottom. And I think what this does is summarize everything we've talked about in the past few videos. That if you have a constant time sum function, Then the antiderivative, you just pull that constant out in front and figure out the antiderivative of that function. You can see how this notation is saying the same thing we said. That's great. Same thing, the antiderivative of sum is just the sum of the antiderivatives. Here is the power rule that we talked about. Here's the 1 over x, its antiderivative being the natural log of the absolute value of x. Remember that one? E to the x, just e to the x, that's great. And then we get into the trig ones. Note they don't list all the different trig functions, just the sine and the cosine, and then the secant squared, secant times tangent, and these two inverse trig functions.